So at this point, we're pretty much done with the first law in conservation of energy in terms of just like looking at it directly. But the first law isn't all that we have in terms of talking about interactions, right? Like if you imagine I've got a cup here, we talked about this earlier, right? But basically, if it's hot, you can imagine giving heat off to the surroundings. But the surroundings are just going to randomly get cold and this cup is going to get hot. And the reason is because of the second law, which basically talks about how certain energy interactions, even if there's a conservation of energy, there's a certain direction that they have to go in. And so in this kind of lecture, we're not going to talk about entropy. We'll talk about that next time. We're just going to look at conceptually how they work. And we're also going to look at things like heat engines and temperature scales and things like that. So even though we're not going to talk about entropy, I do think it makes sense to kind of talk about this idea of like the microscopic argument of what's going on. Even though we're not going to be looking at that, it still kind of helps to have an idea of what's going on. So you can imagine if I have like little balls or little things that represent energy units. In this case, I'm just showing 4 because it's a lot of drawing the more and more you have. There's different ways you can organize it, right? So in this case, I'm showing you, right, there's 6 different ways I could organize this so that 2 of them are on the left. But if I go ahead and I look at only 1 on the left, there's only 4 ways I can organize this. And if I have 0 on the left, then there's only one way that this can be organized. And so if you kind of plot how many permutations you can have based on how many are on the left, when we would have 0, there's only one possible state, right? If I have 2, I think there were 4, right? So this would be 4. If I had, I guess this is 1, right? 1 on the left, and then this would be 2. 2 is 6. And then on this side, I would basically have the inverse, right? So this would be 3 on the left, or 2, or 1 on the right. So that would be the same. It would just be the inverse, and then the same thing with this. And so you can imagine there's a distribution we're going to get, which is going to look something like this. Obviously, that's not exact. This doesn't even go to this point. But the idea is that this kind of central area is much more likely. And that's only with 4 particles. You can imagine if we had millions of billions of particles, this distribution is basically just going to look like this, right? And so the second law is kind of a statistical argument in a way that this is basically what's going to happen. It's almost guaranteed, right? So there's a certain direction things can go in based on the heat transfer. Heat is a less organized version of energy than work, because you can imagine heat is basically just like through a temperature difference. So you have these particles that are kind of moving around all randomly, versus work, which is a force through a distance. So basically they're all going in the same direction. This is ordered. You could also have things like rotational, like torque and things like that. So we can't convert all of this heat into work because this is a more ordered state and incredibly less likely. Basically, once we convert work to heat, we can never get 100% of that heat back to work. But we still can get some of it. And that's the goal of a heat engine, is basically to take heat and turn it into work. So this is a really complicated diagram. This is what a steam power plant looks like. But basically, conceptually, what's happening is that we just have our heat engine, right, which is some system. It has a high temperature reservoir that takes heat in from, we'll just do Q1s and Q outs for now. So this will be Q high. It comes in, and then we also have a Q low. And then we get a work output. And so the representation of Q high here is our high temperature reservoir, which is basically something that has a high thermal capacity, which means that it can transfer a lot of heat without changing a lot in temperature. So basically you can kind of think of this as like an infinite source of heat at this T high. And conceptually it helps a lot when we're deriving some of these ideas, so that's what we use to model it here. Now if we're looking at the power plant, you can see we've got a high temperature reservoir. We also got a low temperature reservoir. So if you just look at this system, kind of bounding box, what we have is we have heat in at a high temp, heat out at a low temperature, work out, and then there's also some work input, but we have a net work output, which is kind of the whole point, right? If we're putting in more work than we're getting out, what's the point of the power plant, So basically what's happening is our fluid is steam in this case, since we're looking at a steam power plant. The turbine, basically it decreases the pressure, and from that pressure decrease, we turn the blades and we get work output. So then we bring this into the condenser, which cools it down. And then we have the pump here, which basically increases the pressure back again. The boiler increases the temperature. and we just keep going in this cycle. There's work input to the pump, which keeps the whole power plant kind of moving, and this is how we get the work output, a net work output of this work out minus this work in. But one of the questions you might ask is like, can we just save the waste energy, right? I mean, what if we just took, instead of this Q out going to some low temperature reservoir, what if I just sent it back here so that I'm not wasting it out to this, wherever this is? This would probably be like a river or the atmosphere, or like a cooling tower, which would be pumping into one of those things. And the simple answer is no. So like if you imagine, basically we've got, this is like a very simple engine. This is like a piston, right? And then we've got this weight, and the work output is basically moving this weight up and down against gravity. So we have, in this case, we have like our working fluid is probably some kind of gas, and we're saying, all right, so we're going to move it, we're going to add heat with a high temperature reservoir, so this is like 100 degrees C or something. Boom, we're going to add heat, that's going to expand it, that's going to do work against this, so we've got gravitational work basically. And then we're going to reject it out to this low temperature reservoir back down, and then we completed the cycle and we can keep going. Now, in order to basically save the waste heat by sending it back into here, what we would have to do is we would have to send energy from this 70 degrees Celsius out to this 100 degrees Celsius, which isn't how heat transfer works. I mean, you could make it happen by basically adding work into it, like you'd have a compressor or something, but at that point, you're adding in more work than you're getting out, so there isn't really a whole point to it. So the simple answer is no. You need to have a high temperature and a low temperature. And in fact, this is one of the statements of the second law. Kelvin and Planck kind of both had different statements that were kind of the same thing, kind of not. And so the textbooks just kind of smash them together. And they're like, all right, here's the Kelvin-Planck statement of the second law. Basically, if you're operating on a cycle, you can't just bring work out from a high temperature source. You also need a low temperature sink. Now, the opposite of this sort of heat engine where we're basically taking in hot, rejecting cold, and then doing work out, is the refrigerator or the heat pump, which does the opposite. It takes in cold, it has a work input, and it rejects hot. So if you imagine the way a refrigerator would work is basically I've got my, like, inside my refrigerator, this is the box, right? And basically I want this to be cold. It'll be at a low temperature, but I want to remove heat to keep it cold, right? So you'd have your little like cycle happening right here, where it would take in cold and reject hot, and then there'd be some work input from like electricity or something, right? In a heat pump, it's kind of the same idea. The way it would work is you would have a room, right, of like your house or something, and I want to heat the inside when it's cold outside. So I'd put my heat pump right here. It would take in heat at a low temperature, and it would reject heat at a high temperature, and it would have a work input, right? So these are technically the exact same thing. It's just depending on which kind of system you're calling your cold area and your hot area. And in fact, an air conditioner is basically just the same thing as a refrigerator, except the refrigerated space is an entire room. Obviously, there's going to be slight differences in like the actual physical implementation because of that. But really, it's all the same idea in terms of like the cycle. Is you've got basically this is really cold, so it's going to actually take heat from our cold space, and then we're going to compress it. That's also going to heat it up till it's hotter than our hot space. We're going to reject heat to the hot space, and then we're going to send it through this valve, which works kind of like what we were looking at with the nozzles earlier, where there is basically a pressure drop, and then there's also a temperature drop. So that can get us back down to a cold temperature. The working fluid in here would be a refrigerant, so something like R134A, because it's able to get to these hot and low temperatures and work with the compressor and the valve in an efficient way, right? All right, and so from this, we can get the Clausius statement of the second law, or I guess this is kind of related. I don't know if you can get it from this. But basically, it says we can't have one of these that has no work input, right? We can't just send energy from a low temperature to a high temperature. In fact, this is actually equivalent to the Kelvin-Planck statement, so you can kind of use whichever one you want. It depends on the situation, what might be easier to work with the other. So if you imagine we've got our heat engine here, right? And it's got an efficiency of 100. And what the efficiency basically is, if we come back up here, the efficiency of our heat engine is the quantities that we care about. How much heat does it give out and how much work does it put in, right? It's really that simple. It's just how much heat, we care about the work output, right? because this is the whole point of the heat engine. And then we're just going to divide this by how much heat do I have to put in, right? And so if this is 100, basically that means that these two quantities have to be equal. If it's 100% or 1, then all of the Q in becomes the W out, which we can't have by the Kelvin-Planck statement. So a violation of that would be that this is equal to 100%. You could also write this as, what would that be? It would be Q, I think it would be Q in minus Q out, all over Q in. Or you could also get the net work if you're looking at, like this power plant example, will be W out minus W in. So I guess I should be more specific. This is W net output. And then thermal efficiency. There's also an equivalent to the efficiency for the heat pump and the refrigerator. It's called the coefficient of performance. Again, it's really all about the values that we care about. So for the refrigerator, what do we care about? We care about how much electricity do I got to spend on this thing, and how much is it going to cool down my cold space, right? So how much basically cold heat can I get per unit of work in? And then for the heat pump, what do we care about? We don't care about how much cold it's grabbing. We care about how much heat it's rejecting. So for the heat pump, basically we would have Q high, Q high over W in. Okay, so now going down to kind of the equivalence of these two, basically what we're going to assume is we're first going to show that the Kelvin and is the same as the Celsius. So if we have a heat engine that breaks this law, it's 100% efficient, and we have our high temperature reservoir right here, what we're saying is that, okay, it's going to take in QH, and then all of that is going to be converted to our work output, which is equivalent to the value in energy of QH. So these energy values have to be the same, right? And then right here, we've got our refrigerator. Due to conservation of energy, this QL coming in and this QH have to balance, so we get QH plus QL coming out. The problem is that if we go ahead and take a look at our system as these two things, so like this right here, and we ignore basically this internal heat transfer, what we have is a device which takes in a QL and it rejects a QL, basically, right? Because we give it a QH and we take a QH, but those basically cancel out, which is a violation of the second statement that we saw. And it also goes the other way. If we have a refrigerator that can basically take from QL to QH, and we imagine this heat engine giving a work output and a heat input, all of that heat rejected at QL could just be turned back into QH if we had a refrigerator that can go straight from QL to QH. So there would be no need to reject at QL because we could just turn it all back into QH. You see what I mean? And so these two statements are basically equivalent, and depending on what you're looking at, it might be easier to think about one or the other. And now we have to talk about reversible processes. So even though we can't get 100% efficiency, the idea here is that we want to know what's the best that we can do, right? So we have an idea to kind of compare our real efficiency to the best that we could possibly have. So a reversible process is basically one that has no net effect on the surroundings. So no like heat loss, nothing like that, nothing changes. And some ways that you can have something that's irreversible are things like friction. You have friction, you could have, it's called unrestrained expansion. So basically if I have like some pressure device right here, right, and I just pop a hole and it goes, psh, it all comes out here and I don't get any work output from this expansion, then I can't get that back. You also have things like heat transfer. So we talked about earlier, if you remember the little particle example, once I take this heat and I disperse it, there's no way to kind of get it back without doing work on my system. So I've basically done something irreversible, right? Because I have to add energy in order to get it back to its original state. And so what we want to look at is something called the Carnot cycle, which is basically a model of a heat engine that's 100% reversible. So it has four processes. The first one is constant temperature expansion. So basically if you imagine, like I've got my piston right here, bada bing, bada boom, and I've got some massive kind of high temperature reservoir out here, and I expand it. So this is going to be the heat addition part. So basically this would be like the boiler or the Q in side, but I'm allowing it to stay at TH the whole time. So basically I'm going to add heat, I'm going to add heat, I'm going to add heat until the inside of here and the outside of here are the same temperature. And then I'm also going to do, step 2, is adiabatic, so that means no heat transfer, so I'd insulate this piston, right? And then I'd allow it to expand some more while it cools down until basically it's at the point where it's at like equal pressure, right? Then step 3 is I would compress it, so this would be kind of the work input, or the QL, heat rejection. So the first step would be at constant temperature, so I'd have my T low reservoir right here, right, and I would compress it. And then step 4, I'm sure you could guess, is you would do adiabatics, you would insulate it and then let it compress even more. And I have a diagram right here of what's going on. This is pressure, this is volume. We expand it at the constant temperature, then we allow it to expand adiabatically, and then we compress it and we compress it, and all of these are idealized as reversible processes. And you can see, because if you remember from a little bit earlier, work is like integral of P dV. We have a PV diagram, which means that the area enclosed is basically the work output that we're getting from here. So when we're going from left to right, we would have a work output that's basically the area under this whole thing right here, right? And then we'd have to subtract the area under, so the area under this top curve, right? And then we would subtract the area under this curve right here, and what would be left is just the area inside this shape right here. So that would be our net work output. Alrighty. And now if you wanted to, you could also reverse this process and you would just get the refrigerator equivalent, right? Because you'd have a QL and a QH rejection. And again, this is the ideal. So when you have a reversible process, it's going to give you the most work output and the least work input going on your cycle, which means that it's the ideal case that we want to compare things to. And so if you go ahead and you look at these ideal heat engines, there are 2 principles that you get. And basically, to sum them up, the reversible, the Carnot heat engine, you can't have a better one, right? So between 2 reservoirs, a heat engine is always less efficient. If it's irreversible, then it's reversible. And secondly, the efficiencies of all reversible heat engines are the same between the same 2 reservoirs. So just to kind of look at the proof for this real quick, if you'd imagine we have 2 heat engines, same reservoirs, things like this. One of them is a reversible one, and we'll go ahead and start. We'll look at the first one, which is the irreversible has to be less efficient. So let's assume that heat engine 1 is irreversible, right? And let's also assume that it's more efficient. So this is going to be like a proof by contradiction. So if we assume that it's more efficient, and also this is reversible, then we're going to go ahead and reverse this process. So instead of a W2 out, we'd have a W2 in, we'd have a Q in, and we'd have a Q out just like this, right? Now we're assuming it's more efficient, which means that this W1 has to be greater than this W2. And also, if you imagine the same QH, if we're getting more work output, then there would have to be less Q low because of conservation of energy, right? And so basically QL2 minus QL1 would be a positive quantity, and also W1 minus W2 would be a positive quantity. And if you imagine we combine these as one singular system, we have a QH rejected and also a QH in, which cancel out, and we basically just have no QH, right? And then we would have W2 as an input, W1 as an output. So our net work is W1 minus W2. And then same thing here. We're drawing Q2 and we're rejecting Q1, or QL1 and QL2, right? And so our combined system would look like this. And if you look, you can see that we're basically converting all of our energy from a reservoir into work. So we're converting heat to work, which is a violation of the Kelvin-Planck statement. And now, if you imagine that instead of this being a reversible engine, we instead had, if it was an irreversible, if we imagine it as a reversible engine that was more efficient, then we would have the exact same argument. So basically, this proof just shows you can't have anything that's more efficient than the reversible Carnot heat engine. All right. So now that we've shown that the Carnot, or the reversible heat engine, is the highest efficiency that we could get, what we want to do is find a way to basically compare a real heat engine to that, right? Like if I've got my heat engine and I know what the work output is, and I know what the heat input is, and I know like how much heat is rejected, how does this compare to the ideal one? And the solution to that is actually related to the definition of the Kelvin scale. So what we're going to do is we're going to go looking for something called a thermodynamic temperature scale, which basically is one that's independent of our setup, our fluid properties, and things like that. So if you imagine if I've got some heat engine, right, it's got a Q in, Q out, and a work output, I want a temperature scale that's independent of my setup completely. So it doesn't actually care about the QH and the QL and the W, because if you imagine if I pump in more heat, then I'm also going to get more heat out and more work output. And it also should depend on the fluid or anything like that. And so the only thing that can change between different setups, besides how much you're sending through, which doesn't affect the efficiency, right, is the temperature of the reservoirs. That's the only thing that's different between our setups in terms of a reversible engine's efficiency, right? And so what we can say is that our thermal efficiency, if you remember, this equals our work output divided by our heat input, right, the two things we care about. And this is, we can go ahead and rewrite this. This is the same thing as heat in minus heat out by, conservation of energy. Since this is operating on a cycle, there's no change in the internal energy, so all of the energy transfers have to balance out. Divided by QH, this is the same thing as our 1 minus QL over QH. And so we can say that, thermal efficiency, we'll say that for a second. Okay, so we just said that our thermal efficiency should be a function of literally just the temperatures of the reservoirs, right? If we want this thermodynamic temperature scale setup, okay? But we also know that our thermal efficiency is just a function of QL and QH. So QL over QH should just be a function of TH and TL. And I'm going to go ahead and invert these just because it'll make things a little bit nicer, I think. QH over QL also has to be a function, right? It would just be the inverse of the other function. Okay? Now let's go ahead and look at the setup right here. What I have is I have a high temperature reservoir and I have a low temperature reservoir, and I've got 3 reversible heat engines. So this one's taken in Q1, it's rejecting Q3, and it's heat engine number C. Why is this one also C? Basically, it has the work output of C, right? This should be a B. Then I've got A right here. It also takes in Q1, it rejects QA, and it has Q2. Basically, Q2 comes out of A and into B, and then it rejects out Q3. We've got work B, and we've got work A. And we also have a T2 here, which kind of represents basically like a in-between system that takes the heat and then rejects the heat at some temperature, just so we know what the temperature between these is. Basically, there's a temperature that this heat distribution is happening across, right? And so if we imagine just by like the rules of division and things like that, our Q1 over Q3, which is basically our high over low for this heat engine right here, right, has to equal, come on, I'll just put a 3 here, has to equal our Q1 over Q2 times our Q2 over Q3. And that's just by like the rules of algebra, right? Because these cancel and we just end up with Q1 over Q3. But we just showed that this is also a function of the temperatures. And so for each of these engines, what we're going to have is that some function of T1 and T3 has to equal some function of T1 and T2 times some function of T2 and T3. So basically, when you multiply across these functions of T1 and T2 and T2 and T3, they have to cancel out such that you just get a function of T1 and T3. And the only way this works is that if your function of T high and T low is set up in such a way that it's equal to just some other function of T high divided by that function of T low. So you can imagine, in this case, we would have some function of T1 over its function of T2 times some function of T2. These would cancel and you'd have divided by some function of T3. In order for this multiplication to cancel out our T2s, it has to be set up in this way. And Lord Kelvin comes along and he's like, hey, what if we just let our function of T equal T? And that is the definition of the Kelvin scale, well, up until like 2019. But this is basically what the Kelvin scale is based on. Is any functions where you can say that basically the heat, because remember this is equal to Q high over Q low. Any function where Q high over Q low is equal to T high over T low in your temperature scale is fine. So we could just, I would said like T equals, T plus 2 or something, right? Or T times 2 or whatever. But this is very simple, and it's the basis of the Kelvin scale. And so what we can say is that if we're using the Kelvin scale, QH over QL, remember for some reversible heat engine is equal to TH over TL. And this right here is where the Kelvin scale becomes really useful, because this only works if we assume this, which only happens if we're in the Kelvin scale, right? And so what we can say is that, okay, if I return back to my efficiencies of the other things, like let's start with the heat engine, right? So my thermal efficiency for the heat engine, I know, is equal to W out, or I guess W net. We'll just put W over Q in. Q in, which has to equal Q high minus Q low, all over Q high, which equals 1 minus QL over QH. But we just showed that this fraction right here, if we're talking reversible, will be the same as TL over TH, right? If we flip both of these. And so this has to equal 1 minus TL over TH. So if we just know the temperature of the reservoirs, we can find the efficiency of a reversible or ideal engine, or a heat engine. And we can also do the same thing for the refrigerators that we talked about earlier. So refrigerators, if you remember, basically the way this would work is you'd have your refrigerator, you'd have a Q low coming in, Q high coming out, and then there'd be a work input, so it's just the exact opposite of our heat engine. And the thermal efficiency for the refrigerator is equal to how much QL we get per amount of work we dump in, which is equal to our QL over QH minus QL, which equals, if we go ahead and we divide everything by QL, we'd have a 1. Basically, if we put a 1 over QL here, right, and then a 1 over QL in the denominator, what we would get is 1 over QH over QL minus 1. And hey, QH over QL, we know that that has to be TH over TL in our ideal case, so this would be a 1 over, right, TH over TL minus 1. And if you go ahead and you multiply through, you would get TL over, right, TH minus TL. If we multiply this top by TL and this bottom by TL. And so now, if we just know the temperature of the reservoirs, we can find the efficiency in the ideal case, and we can compare that to our real one, and now we know how good our refrigerator is, right? And just to be complete, we could do the same thing with the heat pump. So remember, the heat pump is the exact same concept as our refrigerator. We've got our Q low, Q high, except now what we care about is how much heat we're adding, right? Because we're not cooling down a space, we're heating up a space. So what we would have is our coefficient of performance. I might have wrote down the efficiency. This is not thermal efficiency anymore. For refrigerators and heat pumps, it's called the coefficient of performance. Yep. Okay, so this is a heat pump. Heat pump. This would be the Q high over the work in, which is, right, Q. Let me make this a little closer. Q high over Q high minus QL. QL, that's not great, but it'll work. Which equals, if we divide the top by QH and the bottom by QH, we would get a 1 over 1 minus QL over QH. Which we can replace this, if we're talking about the ideal reversible case, with TL over TH. And we're using the Kelvin scale, and then we multiply everything through by TH. We get a TH over TH minus TL. And boom, same thing for the heat pump. If we know the temperature of the reservoirs, we can find the ideal case. We can compare that to our actual case, and then we know how good our heat pump is. So that's it for the second law, conceptually, and kind of in terms of these efficiencies and different types of engines and things like that. Next time, we're going to talk about the second law as it pertains to entropy.